11.4 in the comparison test. I'll go ahead and broadcast to your screens. Let me point out that most of the time that I'm going to use the comparison test in practice as a mathematician, if I come across something and I need it, I actually rarely apply this test that's in the blue box up here. Although it's certainly common and doable, more often than not, I apply this one. Okay, it's called the limit comparison test. I want you to see where the comparison test makes perfect sense geometrically why it would be true. When I say geometrically, I mean if I draw a picture, you'll see, well, yeah, obviously it has to be true. Whereas the limit comparison test doesn't really make as logical of sense by just looking at a picture, but it's easier to do. And essentially, they're both doing the same thing. What you're going to do in the comparison test is exactly what the name suggests. We are going to compare the series that we're trying to answer a question about to some known series. Okay? And so when, for example, I have the series a sub n and the series b sub n, so the sum from n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity for b sub n, let's assume for now they're positive terms. So this is only going to apply in that context. Then I'm going to be able to say that if b sub n is convergent, so this is like my series that I know something about. Let's assume I know that b sub n is convergent, and I know that a sub n is less than or equal to b sub n always. Okay? A sub n is my question, b sub n is my known. That is, I know its properties. Maybe it's a p-test, maybe it's a geometric series, but let's say I already know something about b sub n, and I'm going to compare my a sub n, which I don't know anything about, to my b sub n. Okay? So in the case that b sub n is convergent and a sub n is less than or equal to b sub n, then I will know that a sub n is also convergent. On the other hand, if b sub n is divergent, and a sub n is always bigger than or equal to b sub n, then a sub n is also divergent. I need a little cooler. Okay. Now, if you kind of think of the picture that I've got in my mind here, let me draw it for you. Over here, let's do this Roman numeral 1. Okay? Let's say the top curve is b sub n, and the bottom curve, whatever it's doing, are the terms of a sub n. Okay? If the one on top converges, which means they're getting small enough, fast enough to force the sums, the partial sums, to go to 0, then any sequence that's underneath it, but still positive, would also have to be a convergent series, right? Because the one on top, the terms go to 0 fast enough that if I were to add them up, the whole thing converges. That's what I'm assuming that I know, which means the thing underneath it would also have to converge. Okay? On the other hand, if I was on the other side, let's say the b sub n's down here. Maybe they go to 0, but they don't go to 0 fast enough. Let's say this b sub n is divergent. And I should be careful. I'm actually talking about not the sequence, but the sum of these guys are over here convergent, over here divergent. So if the thing underneath is divergent, then anything up here above, right, the a sub n, would also diverge. Sorry, that's kind of sloppy. Okay, so When the B sub n bounds the sequence above, it's always bigger than the thing underneath it converges. If I knew that B sub n was convergent, but my A sub n was above it, in that case, I don't know anything. I mean, A sub n could converge or it could diverge. If the thing on top diverged, I don't know if the thing underneath it converges or diverges. Okay? Now, in using the comparison test, we're almost always going to have to, well, always, we're going to have to know what some sequence that I'm going to compare it to. Well, I need to know what it does. So just look at this example right down here. I'm going to need to compare this sequence of terms, this series, to something that I know what it does. And the most common choices are the p-series or maybe some geometric series. Because with p-series and geometric series, I always know what they do. I've got conclusive results that I can always tell whether or not a geometric series or a p-series converges or diverges. Okay? So let me walk you through some of the tricks that are commonly used to determine how to compare something like this. So think about 5 over 2n squared plus 4n plus 3. Here's the most common trick. This looks to me a lot like something over just n squared. Now here's what I'm going to do. I'm going to rationalize. I'm going to justify, it's a better word because rationalize means something else in mathematics. I'm going to justify that I can make this term right here comparable to this. Now, if I take this term right here, this whole expression, and I turn it into this, I'm just throwing away 2 terms in the denominator, right? Now, if I throw away this 3, what happens to the size of the denominator? Over here, I'm adding 3. Over here, I don't have the plus 3 over here. I've made the denominator smaller. Right? In fact, I threw away the 3 and I threw away the 4n. So 2n squared compared to 2n squared plus 4n, this over here, this denominator, is smaller than this denominator. For all values of n, no matter what n you plug in, positive, this number here is smaller than this number down here. Isn't that right? So as long as these are pluses here, I just throw them away, I made the denominator smaller. If they'd have been a minus and I threw it away, I made the denominator bigger. Right? But in this case, I made them smaller. Now, if you make the denominator of a fraction smaller, what happens to the whole fraction? It gets bigger. So this is now less than or equal to. Makes fraction bigger. Now, consider, what does the sum of 5 over 2n squared do? Does it converge or diverge? Well, here's the trick on this one. You can take that 5 halves as a constant, just like you do with integration, pull it outside. Okay? So this becomes 5 halves sum from n equals 1 to infinity of what? And what does this thing do? Yeah, if you look at just 1 over n squared, you know it goes to 0. But remember, knowing that the terms go to 0 means you know nothing. But what's the test that I can apply here that tells me that this thing converges? P-series. P-test says this converges. Okay? So if this thing converges, and notice, this is like my B sub n here, and this is my A sub n here. Look at number 1. If B sub n converges, and A sub n is always less than or equal to B sub n, then what do we know about the series A sub n? also converges by the comparison test. The key was I was able to bound this above by some series, by the terms of a series that I knew would converge. Okay, so that's actually a very common trick, and there'll be at least a couple of homework problems where what you do is you just take this guy and you start throwing away terms either in the numerator or in the denominator, but you got to track it so that you get something bigger. Okay? That is bigger if you want to bound it above by something that converges. Maybe it looks like something that diverges, and you want to bound it below by something. You got to try to figure out a way to make it smaller than something, and so forth. Okay, so let's try another one and show you where this can get a little bit annoying and not being as easy as the first one. Okay, so let's look at this guy. 1 over n squared minus 1. Do you think that, just hypothesize, do you think that converges or diverges? What does your intuition tell you at this point? Why? Why are you thinking that? Other than just guessing randomly.
I'm saying part because it's infinitely larger.
Okay. Again, it's going to 0, which is okay. I mean, that has to be true for it to be convergent. But there are ones like we mentioned earlier, the sum from 1 over n, the n gets infinitely large, but this still diverges. Okay? So what about this one makes you think it behaves more like a convergent one than this one? Do what?
The squared.
The square. It's kind of like a p-series, except for that stupid minus 1 in there, right? If it was just 1 over n squared, we'd know it converges, right? But we don't know that for sure. But it has to. I mean, it just makes sense, because when n gets really, 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 really big, that's more like n squared than it is n squared minus 1 is very, very close to n squared. Okay. But here's the problem. I can't do this. Can I? Right? Because if I make the bottom of the fraction, now if I take away this minus 1, I'm actually making the bottom of the fraction bigger, right? Because n squared minus 1 is a smaller number than just n squared. So if I throw away the minus 1 and look at n squared is going to be bigger of those two. And if the denominator's bigger, then the whole fraction is smaller. I mean, if I had done this, that's true, but it doesn't help, right? Because this converges, and you found something smaller than your series that converges, which doesn't tell you anything about the thing above it. It could converge or diverge. Doesn't help. Okay, so we can still do this, but we got to get creative. And this is why I don't like the comparison test as much as I like the limit comparison test we'll get to in a second. Here's how I get creative. Think about n squared minus 1 by itself. Let's just consider n squared minus 1. I claim that this is bigger than n squared minus n squared over 2. It seems like I'm pulling this out of thin air, but it actually turns out to work, because if I can simplify this, I end up with just n squared over 2. But why would this always be true for all n? Well, think of this number and this number, right? 1 and n squared over 2. Start plugging in some numbers for n, right? 1 n squared over 2, that's 1/2, okay? So that's not true for n equals 1, right? That's greater than or equal to. But once I get to 2, right, n squared over 2 becomes 2. If I plug in 3, n squared over 2 is like 9/2, which is a lot bigger than 1. Right? And then 4, 16 squared over 2, 25 over 2, 36 over 2. This is bigger than or equal to that for all n bigger than or equal to 2. And that's where I'm starting from. And notice, if I'm taking something away from n squared, if I take something even bigger away, the whole thing will get smaller. You understand what I'm saying? As I go from left to right here, I'm taking away 1. On this side, I'm taking away n squared. 1 is smaller than n squared. So if I take away something bigger, the whole thing gets smaller. It's kind of like the way the fractions work. The denominator gets bigger, the fraction gets smaller. If I'm subtracting something bigger, then the whole difference gets smaller. Do you agree with that? Okay, so why did I choose n squared over 2? Well, I can actually combine these two. N squared minus n squared over 2. This is like 2n squared over 2, right? Which gives me 2 minus 1, so just n squared over 2. So n squared minus 1 is always bigger than or equal to n squared over 2. Agreed? Now let's see how that helps us. What does that now mean for this fraction? Take 1 over n squared minus 1. Let's replace the denominator with n squared over 2 now. So how do these denominators compare? Which one's bigger? N squared minus 1 is bigger than n squared over 2. So if this denominator is bigger than this one, then this fraction is smaller than this fraction. Right? And what's 1 over n squared over 2? Invert and multiply. You get 2 over n squared. All right, so here now is my a sub n, and here's my b sub n. And how does the sum of 2 over n squared from n equals 2 to infinity behave? Well, that's 2 times the sum from n equals 2 to infinity, 1 over n squared. And as you already told me, this thing converges, which means that my original series converges by comparison test. Again, I found a series whose terms are always above my series, and I know that series converges by the p-test. So this one then has to converge by the comparison test. So this stuff in the middle here, all this in here, to me is, I mean, this what varies from one problem to the next can be challenging. So you don't have, well, you're going to have to at least understand where it comes from. When we get into higher mathematics, we use that kind of stuff a lot. But the good news is there's an easier way. Note, you don't have to write this down, but I'll go ahead and put it there, is an easier way. You can write it if you want to, but and it's coming at the end. All right. Let's do another easy one. Actually, this one's pretty easy. Let's see if you can't figure out what I'm going to bound this thing by. Let's consider 1 over 3 plus n to the nth. What would you compare this to, do you think? want to take away the 3 and look over 1 over n to the n like that? The to the nth thing is a mess, and so is 1 over n to the nth. We don't do we know what this thing is doing as a series? It's not geometric. I mean, just write out the first few terms, you could see it. That would be like 1 to the first plus 1/2 to the second plus 1/3 to the third plus 1/4 to the fourth. It's not geometric. It's not a p series because you're not raising the same power every single time. So, I don't think so. Okay, so if we get rid of the n, well, n's always positive, right? So what does that do to the inside fraction? Makes it smaller in the denominator, so the whole fraction becomes bigger. So you can do this. Do you know what this series does? How do you know? Kyle tentatively said converges.
I'm taking a shot in the dark.
It's getting smaller, but again, that's not enough.
That's what I want to say.
Right? I'm going to say that over and over again. Just going to 0 is not enough. Is it a series of type that we can immediately decide convergent or divergent? Is it a p-test? No. Is it geometric? Is it geometric?
Yes.
I mean, write out the terms if you have to. It's 1/3 plus 1/3 squared plus 1/3 to the third plus 1/3 to the fourth. What am I doing to get to each term? You what? Going up by 1, but to go up by 1 in the power means I'm multiplying by 1/3 every time, right? I multiply this by 1/3, I get 1/3 squared. Multiply this by 1/3, I get 1/3 cubed, right? So it's geometric. Does it converge? Well, what's the R? 1/3, which is in absolute value less than 1, which means converges. You have found something bigger that converges. Again, you see why it's bigger, right? The denominator got smaller for the inside fraction, which means that the fraction got bigger. And if you raise them both to the same power, then a smaller fraction to a power compared to a bigger fraction to a power is something small compared to something larger. So, by comparison, the sum, right, because we just over here proved that the upper series converged. So that means the one beneath it, n equals 1 to infinity of 1 over 3 plus n to the nth, also converges. Let me make one comment, just because you may have had this question in the back of your mind, you didn't think to ask, but did you notice that I had a 2 down here instead of 1? Because 1 you plug in, you get 1 over 0. Now, the thing to remember about a series is actually where it starts doesn't really matter. Right? Whether I start at n equals 1, n equals 20, n equals a billion. The only thing that really matters about convergence is that it's going to infinity. Because infinity is really, really big, right? If I were to post a link on your Facebook wall, I would say, you have no idea how big infinity really is. And that's link bait for you to click. You wouldn't believe how big infinity is. It's big. It's very, very big. It's bigger than anything you can imagine, okay? So starting at a billion, starting at Avogadro's number, 6.02 times 10 to the 23rd, starting with 1 followed by 100 zeros. At a Google, you know what a Google is, right? 1 followed by 100 zeros. You ever heard that before? I mean, that's where they got their name for the search engine. The number Google, Googol. You look at me like I'm crazy. Have you never heard of a Google? Okay. That's a big number, right? 1 followed by 100 zeros. But it's nowhere close to infinity. In fact, 1 followed by a googol of zeros is still nowhere close to infinity. Because infinity is really, really big. Where it starts doesn't matter. It matters what happens as you take the limit. Okay? All right. Although the condition a sub n less than or equal to b sub n, or a sub n bigger than or equal to b sub n, gives us a test for all n, it turns out, for the reasons I was just talking about, we only need to verify that it's bigger for some n greater than or equal to cap n, where capital N is some fixed integer. What I'm saying here is that to say it's bounded above by a convergence series or bounded below by a divergence series for all n is actually not necessary, as long as you can say that eventually, that is, past some point in the series, you've got the top series is convergent. And the one on top only is eventually bigger than what the picture looks like this. Let's say, and I'll just do the top, I'll do these in curves. Let's say the series does this. Okay, let's say the red is your B sub n. And let's say your blue is the A sub n, and it does this. It's up here, it's down here, it's come back up, it's down here, up here. But eventually, at some point, from that, oh, dang it, try that again. Okay, eventually, it's beneath there. So like here's your cap n. And from that point on, A sub n is less than or equal to B sub n. Notice how over here it's not, right here it's not, right here it's not. It doesn't matter as long as it's eventually. That's all that really matters. And then from that point on to infinity, it's beneath there. Then the comparison test will still hold. So you don't need the strict requirement that it has to happen for all n. So even up here, like if I had come up with this problem, remember where I said this had to be greater than or equal to 2? Maybe this had to be greater than or equal to 7, but eventually this was true. This would all still work. Okay. The second note I wanted to point out here is the point I've already made, but the terms of the series being tested must be smaller than the convergent series or larger than the divergent series. If the terms are larger than the convergent series or smaller than the divergent series, then the comparison test doesn't apply. And the example that they throw in the book here is this guy, 1 over 2 to the n minus 1. It's the same problem I had with the 1 over n squared minus 1, right? 1 over 2 to the n minus 1. How does that compare with 1 over 2 to the n? You throw away the minus 1, the denominator gets bigger, so the whole fraction gets smaller. Okay, but this one converges, right? It converges because this is a geometric series. Geometric with r equals 1/2. I mean, it's the same reasoning that we got with the 1/3 above. It's convergent. But this inequality here is useless for the comparison test because you found something smaller that converges. That doesn't help. You need something bigger that converges or something smaller that diverges. Something smaller that diverges or that converges or something bigger that diverges. Neither one of those help. Which is why the limit comparison test becomes a value, because you don't have to bound things above or below with the limit comparison test. What the limit comparison test does is you say, let's try to find a series that I know something about, but when n gets large, behaves very similarly to the one that I'm working with. Okay? Like what I said up here above on the n squared minus 1 one. I had to do all of these cartwheels here to try to get it bounded above by something. But when we first started this, we all of us stood back and looked at that and said, it's very much like 1 over n squared. It's just like 1 over n squared, so it should converge like 1 over n squared does. But finding something above 1 over n squared minus 1 that converges was a pain in the butt. So, what the limit comparison test does is it says, okay, again, take a series that you don't know what it does, and take one that you do know what it does. And now take the limit as n goes to infinity of the ratio of the terms. That is, just divide the unknown divided by the known. And take that limit. Most of the time you're going to end up with something like Bobo Botan eats DC. If it goes to a number, and that number is not 0, it's positive, then the series do the same thing. That is, they either both converge or both diverge. So you choose a series that you know what it does, and then you take the limit of the unknown divided by the known and see what it goes to. If it goes to 0, this test fails. If it goes to infinity or doesn't exist, this test fails. But if you can find one where this goes to a number, then your unknown is going to do exactly what your known does. So like this one down here. Consider this guy. 1 over 2 to the n minus 1. What do you expect it to behave like? Yeah, what other series do you know, or can you figure out what it does, would this one be most like? 1 over 2 to the n. Right? I mean, that's what we were talking about doing up here, but we couldn't bound it above by 1 over 2 to the n, so it didn't help. But why don't we compare it to 1 over 2 to the n? For the record, can you tell me why this thing converges? We already talked about it, but let's mention it again.
Geometric about it.
Okay? 1/2 plus 1 to the second plus 1 over 2 to the third, right? Plus 1 over 2 to the fourth. Right? It converges because it's geometric with r equals 1/2. That's the thing I'm multiplying by to get to the next term. It's 1/2 every time. So, if I apply the limit comparison test, what I'm going to do is I'm going to take the limit of the unknown terms over the known terms. If that goes to some number that's not 0, then this thing up here will do the same thing that this one does. Okay? So take the limit as n goes to infinity of our unknown divided by our known. So let's simplify this algebraically. What does that become? So just invert and multiply. Dot flip, as my high school teacher wife says. Jot, dot, and then flip the bottom one. Now what I would do to do this analytically is I'd multiply by 1 over 2 to the n on top and bottom, because that makes it easy to find the limit. You could also do L'Hopital's rule because it's infinity over infinity. you may be able to just look at this and tell what you think it does for large n, because when n gets really big, the bottom and top are almost exactly the same, right? That -1 doesn't do hardly anything. So if I multiply by 1 over 2 to the n on top, I get just 1. On bottom, I get 1 minus 1 over 2 to the n. And when you take n to infinity, this thing down here goes to 0, so you get 1 over 1, which is okay. Now check back in the theorem, right? It says you got an unknown series and a known one. I took the limit of the ratio a to the n, a sub n over v sub n, and I got a number c that was finite and positive. So then, by the limit comparison test, what's true? Well, our unknown series does the same thing as our known series. In other words, n equal 1 to infinity, 1 over 2 to the n minus 1 converges. Right, because it converged up here, it converged down there. Done. I didn't have to bound it above by anything. I just had to be able to take a limit at infinity. All right, let's reinforce this. Let's try one more.
It's so much easier.
This nasty, ugly thing is just a rational expression inside, right? A polynomial over a polynomial. Now, if I stood back and looked at this, it's actually not very hard to see what's a good idea to compare it to. I mean, again, the question is, what does this behave like for large n? And if you look at this term, which is the dominating term on top, when n gets really big, the top is going to behave like n squared, because n squared gets a whole lot bigger faster than the rest of these terms. And the bottom is going to behave like n to the fourth. This is like an n squared term over an n to the fourth term, which means n squared over n to the fourth is 1 over n squared. It's going to behave like 1 over n squared. That's where I came up with this. But I don't have to worry about now bounding this above. I can just apply the limit comparison test. Okay, let's try the limit comparison test, which means take the limit, as n goes to infinity, of the unknown n squared plus 2n plus 3 divided by 3n to the fourth plus 7n to the third plus 11n squared plus 13n plus 17 divided by the known, 1 over n squared. By the way, what does this do? Converge or diverge? By, what's your reasoning?
No.
P-test. Because it's n to the p, p's bigger than 1, it converges. So yeah, just multiply by the n reciprocal, that is, 1 over n squared becomes n squared over 1. You get n to the fourth plus 2n cubed plus 3n squared divided by 3n to the fourth plus 7n cubed plus 11n squared plus 13n plus 17. Now, what is the limit of this rational expression? how did you get 1/3? The main term on top is into the fourth. The main term on bottom is 3 into the fourth. So you can do dominating terms. In the little trick I taught you, which one is it? Bobo, Botan, or each DC? Each DC. Exponents are the same. Divide coefficients. Answer's 1/3. Does that pass the limit comparison test? We got a limit that's non-zero, which means the sum from n equals 1 to infinity of this thing here, I'm lazy, I'm not going to write it again, converges by the limit comparison test. And we'll stop there.